So for the first talk, I wanted to give you guys an overview of how you can use, hey man, how are you? Good to see you. How you can use C++ to write C&O tools. So for better or worse, C is kind of like the lingua franca in this environment. It's an amazing language that's been around for a really long time, and there's a reason it's been around for a really long time. It's very good at what it does. But in a lot of ways, it's like a mid-level assembly, right? Helps you write cross-platform code. Most of the time, you don't have to write in assembly. But you're still very much in the weeds, and sometimes unnecessarily so. And what C++ does is it helps lift the programmer out of some of those like in the weeds kinds of things, and allows you to deal in like higher levels of abstraction so that you can build cool things quicker. Not only that, and C++ has been around for a long time, but there's a little bit of like a renaissance that's been going on in C++, which is awesome. So they call it like modern C++. Basically, there was a new revision to the language in 2011, which made the language much more usable and ergonomic, and it feels a lot more like Java, which is kind of crazy. And they've released new versions of the language every 3 years since 2011, and there's a new one coming out in 2020, this year, that it's insane. It almost looks like Python. It's really crazy. Now, they're still like adhering to the principles of C++ where everything's super performant, you have control when you want it, but they've figured out ways of, again, lifting the programmer's thinking above, and you get these what they call zero-cost abstractions. So, I thought, given present company, it would be a lot of fun if we just built a stage 0 implant together using only modern C++. To temper some expectations, there's like no OPSEC things in here. This is purely from a functionality perspective, showing you like how you could build the tasking and results frameworks and multi-threading and do comms and all these sorts of things. So if you're looking for like super cool techniques, we'll have to go elsewhere for that. But I thought, like, let's make a cross-platform beaconing stage 0 implant, and we'll just use straight up modern C++. So because we're using C++, this is going to be cross-platform. You can Windows, Linux, Mac, whatever you got. So if you have a laptop, there's a GitHub repo. It's open now, so you can just pull this thing down and read through it as we go. But basically, we're going to walk through essentially every line of this thing and talk about all of the different C++ features that I used, and you're going to be like, holy crap, like that would have taken me like 300 lines of C to write, these two things that you just imported a header and made it happen. So if you're not super familiar with C++, like there's going to be a lot of details that you're like, what's going on here? Don't fret. I put like some references in my book about like where you can read about all these different things. I gave Skylar a link. We'll distribute later, I guess.
It's in the Slack channel for HEC. I can make sure it gets to the other organizations afterwards.
That's great. So there's all the slides for the talks. There's a copy of the book in there, so that like if you want to go back and you're like, oh, dude, that stood variant thing was awesome. Like I want to check that out. You can there's a page reference. You can go read about it. Awesome. So let's talk a little bit about how we're going to make this implant work. So the focus here is not on what's going on the wire or in the command and control server. So super simple, right? We've got an implant. We've got our command and control, and we're just going to use HTTP posts to send our results from the implant and JSON back and forth for like tasks, and we're going to keep it super simple, right? So like our results coming back from the implant will have like a UUID. See if I can get this working. All right, we'll have a UUID here for like what the task was that you guys are like familiar with how stage 0s work, and okay, cool. So the CNC is going to send taskings down to this thing. The implant's going to do stuff, and then it's going to report back on how things went, right? So the wire protocol looks something like we'll have a UUID, some contents, just like a string, and then like a success, like true or false kind of deal, right? Super straightforward. Any questions about what the wire protocol looks like for this? Tasks, same kind of thing, right? We're just going to use straight up JSON. It's just a JSON list. So you're going to have different kinds of tasks. We'll talk about how we make this work. I think you'd be pretty excited about it. And then like essentially just a bag of key values that'll help the implant know what you want to do with that task, right? Really, really straightforward. I'm sure you guys, many of you have built things that look a lot like this. May not have been JSON, maybe it's some other serialized protocol, but this is super simple. And it'll help with my demos because I can show you the wire. So, cool. So we're going to start the C++ talk with Python. I need some infrastructure so that we can make this implant work. So we're just going to use straight up vanilla Python 3. I think actually Python 2 support ended like a couple of weeks ago. Yeah. Rest in peace, moment of silence, man. So I'm only going to use these modules, and honestly, I didn't even need to use the OS one, but it's just going to be super, super simple. We're gonna make a server that essentially just reads files off disk for tasking. I didn't even do any database stuff. Like the focus is not on the command and control for this; it's on what's going on the endpoint. So we made this really, really straightforward. Cool. So looking at the Python, it's super simple. Have any of you used, speaking super simple, have ever you used a simple HTTP server to like move files? I know all of you have. I'm using the like thing underneath simple HTTP server as the command and control for this. So it's like, you know, really highbrow stuff. So this HTTP server, like when you invoke it as a module in Python, there's like an entry point that it'll just configure one for you and serve a file system essentially. Hey Nish, what's going on, man?
Hey, what's going on?
But here we're gonna provide our own handler basically. So the framework is gonna do all the dispatching of the HTTP stuff, and then we get to inject our own class to do the actual work. Instead of serving files, it's gonna serve implant tasks. Yeah, so in like the PyDocs, you can check out like how to make your own handler here. It's pretty straightforward. You write these like little methods that start with do underscore, and then you put like for posts, if you want to handle posts, you write post. If you want to handle a get, you write get. It's like meta programming stuff. It's pretty cool. So what we're going to do is we're going to handle posts. So our implant will send an HTTP post. We'll pull the content length header off of it, and then we'll try to do our handling of whatever the implant sent. You guys relatively familiar, it's not super important, but if you're relatively familiar with HTTP, this is like straight how it works. There's no like super gangster like subliminal like channel things going on here. We're just posting data. And then there's this other class that we'll talk about in a second, the task manager that manages tasks, go figure. So in the handle results, we have, we take the content length, we put it to an int, we read that many bytes off of the HTTP connection, JSON loads, parses the data as JSON, so now this results thing is a dictionary that we can interact with, and then we just handle those results, and then we're going to save a little bit of data about the client that sent, you know, for logging purposes, like what address it had, the date time string. And then we send a 202. Anybody know what that code is? No? Okay. And then we write the result to a file. So basically this thing gets a post, it does some stuff and sends like new taskings, and then it drops the results to disk. It's very straightforward. Okay, finally, how do we handle those tasks, right? So this results object is a dictionary. It's a dictionary of the results that we got back from the implant. There's like a key that's a UUID, and then there's a bunch of stuff that it reported with, hey, I was successful, I wasn't, whatever. So it's going to take a task event, it's like a folder that you want to like store the tasks in. It'll read that file in, load it into JSON, and then it'll basically build a dictionary, adds UUIDs to the tasks so we know what they are, and then it sends it. That's it. Easy peasy. Yeah. Any questions about that? Really straightforward. There's no magic here. Cool, first demo. All right, so what I'm going to do, just to show you that this works, is this is like a sample results that might come back from an implant, right? So the same format, kind of a little hard for you guys to see, but it's JSON, right? Same format that we talked about, where you've got IDs for the taskings and then some stuff about them. So what I'm going to do is I'm just going to curl this at the CNC server and show you that it processes the taskings. And then we'll talk about C++, I promise. Okay. So we'll run the CNC server. Sweet. So in the server, there's that tasks.json. That's the new taskings that we're going to send down to this this implant. Sweet. And okay, so we're gonna. You guys know. I'm sure you know how curl works. You've got. We're gonna do a post here, and then we're sending it to localhost. It's the CNC server is bound to port 8000, and then we send the contents of that JSON file. There we go, and we see the response is something that looks a whole lot like taskings, right? Okay, I promise that's all the Python we're going to talk about. Any questions so far?
What did the 202 mean?
Oh, it means like update accepted. It's like 200 okay, but like there's special codes for.
The online says it's been received but has not yet been activated.
Yeah, perfect. I was asking because I don't actually remember. Let's talk a little bit about beacon loop. So when you have a beaconing implant or even a call-in implant, you have decisions to make around whether you want to deal with threading, right? Good reasons that you may or may not want to thread, like if you're on a resource-constrained environment and you know that you're not going to be sending like very long-term things to the implant, and you're careful about the payloads that you send, you might be able to get away with a single thread, right? This one thread of execution services all of the incoming or outgoing communications. It also executes all the taskings that you give it, and it has the advantage of being very simple relatively, right? You're not worrying about any kind of like race conditions or locking or any of that kind of stuff. This is C++ talk, so like I gotta like flex a little bit on the threading stuff. So we're going to have two threads in this implant. There's going to be a beacon thread and a service thread. So the beacon thread is responsible for beaconing, and the service thread is responsible for servicing tasks. That makes sense. So what I'll do here is just talk you through how these two threads kind of go through their daily lives and how they communicate with each other, so that like when we start to piece this thing together, you have context for what each thing is doing. So beacon thread, that's the B, the prefix B is which thread is doing what step. So B1 is pulling results from a results queue. So we'll talk about what this data structure is, but it's basically a thread-safe repository for the results. So it'll pull those, that's the first step. The second step is that it pushes the results to the CNC server, right? And we just saw how to do that with curl, basically. The third thing is it's going to pull tasks, right? So that's the response from the server that you get a JSON blob, and it's going to have to marshal that. And the fourth thing is it pops those tasks into the queue, and then it goes to sleep for a while. Really straightforward. It's nothing complicated, right? Just doing an HTTP post, pushing some stuff up, pulling it down, and then shoving it into a queue. But you'll notice that there are two gotchas when we're doing the threading, which is we have a pull from this queue, right, and a push into this task queue where all kinds of horrible shit can happen, right? If you're not careful, you have to make sure that you do things in a thread-safe way, or you can get all kinds of crazy behavior. Any questions about the beacon loop, how that works? Okay. The The second one is the service thread. So this guy's going to be responsible for tasks, executing the tasks. So step 1 is going to be pulling tasks out of the queue. Step 2 is executing those tasks. Step 3 is pushing the results into the result queue, and step 4 is sleeping for a little while. Not rocket science here, right? Like conceptually, this makes a ton of sense. But like if you've ever tried to write this in C or good God assembly, like you know that there's a lot of difficulty with critical sections and making sure that you're doing things right, and sometimes you're not even really sure that you got it all correct. So I think when I show you how to do this stuff in C++, you'll be very pleasantly surprised at how straightforward it is. Okay, so here we get to, there's like, well, it's like super inconvenient placement of the monitors.
Hold on.
You guys just pull them over. Sweet.
Lay it down.
There you go.
Cool. So, like I said, there's a lot. Like, the point of this is a tour. You won't be experts at this stuff with one talk, but to get you excited about like, oh, I want to go learn more about this thing that looks really cool. I'm gonna explain like what the code is, what it does, and then like a very high level explanation of like how you use it. There's some references down here to different things that you can like go and read about this stuff and work through some examples. So the first thing we'll talk about is this thing called Boost Program Options. So as I mentioned, this is a pretty like low brow from an OPSEC perspective implant. Like it'll have command line options and tell you how to use it so that we can demo it and stuff. It's not like some fancy loader or whatever. So program options is amazingly useful when you're writing your own tooling because basically you can define, it's similar to like program options in Python where you just define like what are the arguments that this program takes, and then the framework just handles dealing with turning argc, argv into some meaningful structure that you can interact with at a very high level. Does that make sense? I know you've written like parsers in C to like parse argc and argv, and it's just like a mess every time, right? So the syntax is a little funny. It's kind of dense, but just to give you again a high level overview, and you can read more about it. You have this options description object class where you essentially tell it, hey, this is what I want you to prompt the user with. Like it's going to say implant, and then you give it options, right? And then you can add options using, they call this a Fluent API. If you've ever seen this in like C# or Java, some people call it a train wreck API. Basically like chain calls together, and the way the API is designed, you call the function and it returns a reference to the same function so that you can keep invoking it. I think it's fine. But here you basically just keep passing it your options. That's actually a bug. That should be something besides H. But and then you tell it, this is what I want the name of the option to be. This is where I want you to store, how I want you to store the data. If it has a default value, you can give it a default value, and then give a helpful string to the user. And so just by doing that, you set up Boost Program Options so that it knows what your intent is for this program. Syntax is, again, it's a little dense, but if you just sit down and kind of learn how it works, it's not that bad. Parsing the options is pretty straightforward. You basically pass, this is a Boost Program Options function called parse command line. You pass it argc, argv in your description, and it stores all your variables in this variable map object here. Yeah, so pretty straightforward. You can try to, it'll try to parse these out of your argc and your argv, and then if it runs into any issues, it'll throw an exception, and you can just tell the user that you got an exception. Pretty straightforward. And then you can do how you access the options that the user passed in from the command line is through this variable map thing. It kind of looks exactly like a Python dictionary, right? Like you just use the square brackets and you give it the name of the option that you're trying to pull out, and then you're good to go. So in this case, we're going to check and make sure that it gave us a host and a service, right? Like a host and a port, so that we know where to reach out. Pretty straightforward. So once we've parsed the options and we've checked them for sanity, now we're ready to like launch our implant, right? So you've got a a host variable, a service variable that we pull out of the variable map, easy peasy. There's this thing called Boost ASIO IO context. We'll talk a little bit more about that. But ASIO is a networking framework. It's actually a candidate for once C++ eventually gets a networking module like in the standard library. This is one of the candidates for how they'll do that. So it's worthwhile getting to know it. This IO context basically handles all the threading and dispatching of network stuff. If you ever used like in Windows asynchronous communications or async IO, overlapped IO, it's similar to that. So we pull out the host of the service, we pass host, service, and IO context to our implant, and then we call serve, right? So this is the entry point of our program. Parse some options from the command line, throw them into, check them for sanity, throw them into the implant, and then we're off to the races serving. And you'll notice, you wrap all these things in try except blocks so that you get nice error messages when things go bad. Any questions about this? Yeah, go for it.
What is Boost?
Sorry, I should probably talk about that. So C++ is two things. It's a language, and it's also a set of functionality that comes with basically every standards compliant implementation. So that's the standard library. And the standard library's got things that you could write yourself, like you don't need to dig into the compiler to make them work. You can just write code and replicate the standard library. But like, why would you do that, right? They've got amazing algorithms, containers, utilities that a lot of really smart people have worked on for decades to get right. So like, rather than writing your own quicksort, you just use sort in standard library, right? There's a very long and arduous process for things, for good reason, for things to get into standard library, because if it's there, it's going to be there forever, right? And every compiler implementer has to make it, and so it's really hard to change if there are problems. So there's a group of libraries called the Boost libraries. If you go to boost.org, and there's like, I don't know, there's over 100 of them at this point, but they're like still very well designed, and there's like a review process for them, but the bar is much lower for somebody to release a Boost library. Oftentimes, things that make it into the language, into the standard library through like the proposal process, started their lives in Boost. So it's like a kind of field team for features to make it into the standard library. Super cool. So in the book, I basically use Boost and standard library together because I feel like as a developer, you should be comfortable with using a lot of Boost libraries because they're just so useful, even if they're not in the C++ standard library. And at least know like when you're about to say like, oh yeah, I'll write my own program options thing. It's going to take me 4 hours. Like you know the time you're wasting. Does that answer your question?
Yes.
Okay, awesome. Yeah, sorry. So you can tell when I'm using a Boost thing based on the namespace, which C doesn't have namespaces, but these essentially are similar to like how the module naming system in Python works, right? Like you've got, or Java or whatever, you've got how many times have people written a class called results, right? I mean, like, so the problem, one of the problems in C is that like if I define a struct called result, like I might have some problems because it can like, mess with other translation units when I go to link them together. Doesn't happen in C++ if you use namespaces. So if you see a namespace that starts with Boost, you know that it, that's comes from Boost. Any other questions about this? Cool. So this is the entry point, kind of like the jumping off point, so you understand like where the program started. This is what the class looks like. So we basically created this implant, and the implant has a definition, and this definition tells us like how the object works. So in C, you have a struct, and this is essentially like a heterogeneous array, right? Like you have different objects packed on top of each other that may have different types, right? A C++ class can also be that. It's like a superset of that functionality, but it also includes things like methods, constructors, and access controls, which are super interesting. There's no way that I'm going to get through how C++ classes work in detail in this talk, but I'll give you a high-level overview so you can see some of the power behind it.
Are you passing host and service by value for clarity, or is there something in new C++ where that wouldn't be by const reference?
Yeah. So it's a great question. So you have a couple of options for how you pass strings around in C++, and with C++ 17 there's even more. So I will show you why I pass by value here, but essentially in the private members I'm going to store these values, host and string. So I have to store them from somewhere, right? And so by passing by value I can move them from the constructor into the fields and essentially like guarantee that I only copy once. And sorry if this is a little in the weeds, but it's a good question. So that's why. So you can make it. There's another one called string view that we'll talk about in a little while that just came out in C++ that makes this even better. But yeah, so these are the question was there are different ways of taking arguments in C++. By reference and by value. So you're probably familiar with these. Like in C, you can't pass a struct or return a struct, right? You have to use references to do that. Well, in C++ you can. It has value semantics, so you can pass things by value and it'll just do copies for you. The way I wrote this, it takes them by value because I'm going to save them. Cool. So this is the constructor. We'll talk a little bit about this constructor, but there's a whole chapter dedicated to how object lifecycle works. Super important if you want to get into C++ to know how object lifetimes work. If you've ever had like a use after free in C, they're terrible. They're really hard to debug sometimes. You don't get those in C++ when you know how the object lifecycle works, because the compiler just takes care of everything for you. All the allocations, deallocations, initializations, everything, it takes care of it. The constructor plays a really important role in that we'll talk about in a little bit. So this is what the one definition would look like. So Chief Shell was asking about why I pass by value. There's this really cool thing called move in C++, which also has a terrible name. Basically, intuitively, it takes the memory that an object is using and allows you to steal that. So like if you've got a big, huge buffer that you're pointing to, and you want to change ownership of that, you want someone else to take care of that, you can just swap pointers rather than having to make a big copy and then give someone the copy. And that's what move does. So here, if I pass in a host and a string, this class will just kind of steal those and store them in the members. And so that way I make sure that if you pass me a temporary, I can just take ownership of them, and I only have to do one construction.
The curly brace initialization, when did that?
Yeah. So it's called braced initialization syntax. There is a really good reason for it. Basically, there are two things. One is in old style C++, the constructors would try really hard to make things work. And so sometimes you would get what's called a narrowing conversion. So you have like a 64-bit integer that would like silently truncate into 32 bits. Like what could go wrong? Braced initialization does not allow that. You'll get a compiler error. And then the other thing is there's something. Have you ever seen Scott Meyer's C++ book? It's called The Most Vexing Parse. So you can make a constructor that doesn't take any parameters, and when you try to use it, it's identical to a function declaration, which causes a lot of problems. So brace initialization takes care of that as well. That chapter 4 talks a lot about why they made this choice. As a rule of thumb, use brace initialization.
And this was added in 11 or 14?
11. So these are the parameters, right? These are just like any function, and just like any other function, you can pass things in to a constructor. These are called member initializers, so they're pretty cool. Basically, a lot of when you have a constructor in, even in Python, right? Your init function, you're just storing values into the object, right? Like that's a lot of what initialization is. Member initializers are really cool because they run before the body of the constructor, and they allow you to use something called const, right? If you've ever used const. So if you have a const member, you can initialize that const member using member initializers. So it's really good practice to anytime you're just setting values, you use it in this member initialization syntax. And then actually, I didn't even need anything in this body, right? Because I was just, all I'm doing is setting members.
Yeah. This in your closure, that's valid before the constructor body?
It is, yes. Yes, it is. So you can get pretty subtle bugs here. The member initialization list like this proceeds in order. So that's guaranteed. The order is guaranteed. So this is the last thing that will launch. And so what we're about to talk about is called class invariants. All of the class invariants will be established by the time this thread could launch. But that's a really good observation. And we'll talk about lambdas a little bit. That's this syntax here is basically a named function. So if you've ever used lambdas in Python, it's a similar thing. They're so useful. C++ constructors establish classes. That's the big mantra. Like essentially, when you design C++ classes, they guarantee some things, right? Like maybe your class is an implant, and you want to guarantee that the dwell time, the time in between beacons, is always greater than a minute or something, right? Hey man. So that could be a class invariant. That's something that you want to enforce, that for the lifetime of your object, this thing is always true, right? And so constructors establish those things for you so that you don't have to constantly be doing error checking whenever you're interacting with the class. Does that make sense? And they're just guaranteed class properties. So here are two, we could probably think of more, but here are two that I came up with for when we're designing this implant class. One is that the service thread is always running. So like, as long as this class this object is up, there's a thread behind it that's constantly pulling tasks out of the queue, right? That's one invariant. A second one is that the members are initialized with sensible values, so things like the dwell time, right, like is non-zero. Maybe that's something that we want to enforce. That when you construct the object, the flag for whether the implant should be running or not is true, like things like that. So constructors are great for that. There's also really, obviously one of the really powerful things about objects is that they expose methods, right? So methods are just functions that essentially like have a reference to an object that they can interact with. So for our implant, we've got three that are public. There's a serve that you saw in main. That's the thing that we were calling after we set it up. And then you've got these things. Anybody know what these are referred to generally in programming? Setters, right? Getters and setters. So we use these because we want to ensure class invariance, right? So you could expose these. So I'll show you the members, but there's variables, methods, fields behind these. There's members. You could just set those. I mean, we could design it so that those things are public and anybody can kind of just change those. But you can see how that could get kind of bad, right? So if I set, what does a negative mean dwell time mean, for example, right? Like that doesn't make any sense. So setters help you to ensure that you're never getting your object into a weird state. It's another really nice feature of using C++ classes. So, for example, we'll talk a little bit about all the fancy pants statistical stuff that's in C++. But like, you know, if you've ever had to write like a triangle distribution in C because you don't want your beacon times to all look the same, just use a standard library, man. You know, you got exponential distributions, fancy stuff, really fancy. Try to pick that out of Splunk, you know. So we can just take in a double that's like the average time to beacon and then do all this fancy pants stuff in the background, and the user of the class doesn't have to deal with any of that, right? Super cool. And it can ensure class invariance. This one actually does, there should be some error checking in there for the mean dwell time, but exercise to the reader. Actually, I think that might throw an exception if it's negative or 0. So I don't know. Another exercise for the reader. And then, you know, set running, this one just kind of is a pass-through, but maybe in the future we want to enforce some things about you can't shut it down unless the task queue is empty or something like that, right? It gives you a seam to control the API. Okay, cool. And then I'm going to give you like a super quick overview of what other members we stuffed into this class to give you an idea of all the awesome things that we're going to like talk about in the next hour or so. So these are all the private members on the class that like the user doesn't have to worry about, but you'll see them when we talk through them. There's a whole bunch of threading related stuff that's super cool. So do you have any JavaScript ninjas in here? Nobody, really? Okay, all right. Let's get some looks. Yeah. All right. Futures? Yeah. Futures? No. Okay. Futures are a way of interacting at a high level with a thread. We'll talk about. Mutexes. You guys know what mutexes are, I'm sure. Atomics. Pretty cool. Vector. It's a container, right? And then a property tree. I'd be really surprised if anybody's heard of that. These are cool. So these are like key value stores that you can store INI, JSON, all kinds of things. We're going to use it for basically JSON parsing. It's pretty cool stuff.
Is that essentially a registry in memory?
Exactly. Yeah, it's a great way to think about it. It's actually, so it's like JSON is a subset of the things that you can do with the property tree. For the beacon loop, we've got two methods to help kind of break up the flow so our functions don't get too big.
What's the annotation?
It's called an attribute. I'll talk about those. They're pretty cool. But basically, it gives the compiler a hint that like if somebody calls send results and drops the string on the floor, like give them an error because they probably didn't mean to drop it on the floor. Like if you don't take your taskings, like that's bad. And then the service loop. So this is the target. If you remember in the constructor, there was that lambda. We pointed the thread at something. This is the function we'll talk about. And then for beaconing, you've got all your beaconing related members that you need to be able to communicate, to determine what your dwell time is, yeah, all that kind of stuff. And then some references to all the different classes we're using there. Cool. So this is a super simple beacon loop, right? So it's just a while loop that checks every time if we're still supposed to be running. I'm sure you guys have written this a million times. Interestingly, this is running is an atomic. I'm sure you guys have used atomics before. Are atomics and volatile the same thing? Yeah, no. Don't use volatile. You should use atomics. So basically, this makes sure that any access to the variable happens in one logical step, basically, when you're thinking about the concurrency, and also that it's visible to all the other threads. Otherwise, compilers are allowed to do some crazy stuff to optimize, and you'll end up with crazy bugs. You don't have to worry about this because this is C++ and you just made it an atomic and you go on with your life. But if you're writing this in C, you have to think about all kinds of important stuff like that. Cool. So in the beacon loop, we just do two things. Send the tasks, send the results, you get the tasks back, and then parse the tasks, right? Remember that diagram of like how the beacon loop works? pretty straightforward. And we don't have to deal, I mean, you've seen in C how every time you make a function call, you have to like check for errors on stuff. We don't have to do that here because we use exceptions. So if there's anything that's like really bad that happens, like the network is down, it just throws an exception, we'll log it, and then continue on with our life. We don't have to keep checking for it. It's pretty cool. Right? There's your exceptions. And then we have to determine how long to sleep until our next beacon. All kinds of options for this. I showed off a little bit with some of the standard library features, but here we're calling this dwell distribution. This is an exponential distribution from the standard library. So it's going to give us a variable, random variable that has the exponential distribution, which is like used in inter-arrival times, right? So it would be really difficult to tease that out if someone was doing fancy analysis of network traffic, for example.
What's the
For the-
device there?
Oh yeah, device. So the standard library has to service many different communities of developers. So it has to deal with game developers, science, mathematical, computational scientists, and system programmers, cryptographers, all that kind of stuff. It turns out the definition of random is a little like elusive in computing. So there are many ways to get random numbers, whatever that means. So to a scientist, we actually if you're doing computational statistics or fluid dynamics or something like that, you actually want repeatable randomness, which sounds insane, but you want people to be able to reproduce your like simulation study, for example. And so you might use a random, like an entropy engine that has random seeming numbers, but that are like, have a pattern. Mersenne twistor is like the really popular one that you'll see out there. These are called like pseudo-random number generators. Super fast, like have really like long, like really desirable properties for simulations and things. If you end up using one of those for like cryptographic purposes, it's like it's horrible. Like it's the source of so many of the vulnerabilities you see out there. Is like you use a secure crypto system, but you feed it random numbers that come from like a predictable seed, and you just completely blew the crypto system out of the water, right? So there's another device that's in the standard library that's called random device that actually uses the operating system or the environment to feed it random numbers and sort of like punts getting good random numbers off to the operating system. Sorry, it was a super long answer, but does that answer your question?
For doing your error handling with
Yeah.
exceptions, like it used to be taught that exceptions should be exceptional because they're expensive. Has the thinking changed
Yes.
because they got less expensive, or just because the readability has been improved?
Yeah, it's a great question. So you should do both error checking and exceptions in your code. And it's more of an art than a science, like when you use one versus the other. Are you all familiar with exceptions? Like Python exceptions are a perfect proxy for like how C++ exceptions work. So the shtick with exceptions is they're faster when things go right because you don't have to check for errors, and they're correct when things go wrong, right? And so if the error that you're trying to check for is something that like happens very rarely and is something that like when you're doing a task, the exception is so fundamental, like you're out of memory or like the network is segmented or something, that there's like no way that as I'm dealing with like a get file task, I'm going to deal with a network segmentation, throw an exception, because then you're going to handle it in the right place, and you're not like littering your code and your runtime code with all this error handling junk. On the flip side, if for example, like I'll show you a recursive directory walk. If I hit a file where the permissions are set so that I can't access it, that's something I should anticipate, right? Like that's going to happen pretty regularly. Like check for that error and handle it locally somehow, right? So you do both is the short answer to your question. There's a chrono library in C++. It turns out calendars are really complicated. I don't know if like you've ever tried to like write the Gregorian calendar in a programming language, but it's like non-trivial, like how difficult it is. dealing with time conversions and all sorts of craziness. So it's a little verbose, but the Chrono library is pretty impressive. So here we're able to essentially like create a seconds object out of this double that came out of the exponential distribution, and then we call basically sleep for that amount of time. Pretty straightforward. Any questions about any of this stuff? Feel free to interrupt me. It's totally freeform. Cool. So that was the beacon loop at a high level. Let's talk about the service loop at a high level. So you'll notice again, there's this while is running, right? Like there was one in the beacon loop as well. Here we see this vector with this kind of interesting syntax. Do you know what these angle brackets are? Has anybody seen these? How many of you seen these?
Templates.
Templates, that's right. So C++ has some of the best generic support of any programming language. So generic programming is the ability to write code once that works against many types. So in strongly typed languages, this is a really important thing. In Python, you don't give a shit because everything's a duck, right? You just like program and like the interface is whatever you define it, and at runtime, it's going to find the method that's like patched onto that object or whatever. In compiled languages, we care a lot about types because it helps to eliminate whole classes of errors that like you, and C is a mostly typed language. It's like strongly typed, weakly enforced or something is what they call it. So generics are a set of techniques for writing code that works against many types. In C++, you have a couple of options, two options for how to write generic code, and it depends on whether you're making the language do its work at compile time or at runtime. So at runtime, you have these things called interfaces. Like if you've ever written in like Java or C#, that's just like how you get it done is with interfaces. You have those in C++. You have to do a little bit of work to get them. Super useful if you ever write like a plugin framework, for example. But you can do that dispatching at runtime. The preferred way is with templates. So with templates, we have this syntax where essentially std vector is a type. It's a container. But it's written without regard to what it's containing. We can tell it what that type is by putting that type in angle brackets. That's like the high level of how templates work. And you can make your own templates, like totally, especially if you're writing a library, you'll end up writing a whole lot of templates. But yeah, these are super cool. So basically we've created a vector of tasks. This is a sequential container, so it's like an array, but it can grow and shrink. So there are pluses and minuses. There's places for arrays, there's places for vectors, but this basically has an unbounded size until you run out of memory. So this little switcheroo is we're gonna hack our local tasks from that queue that the beacon loop is stuffing tasks into, okay? I'll show you how that works, because remember, we have multi-threading here, so it's like you gotta be very careful. And then we're gonna service each task, and then we're gonna sleep for a second here, right? I don't think there are many other ways to do this, pretty straightforward. So how do we acquire tasks from the queue? So, have any of you guys written multi-threaded code in C? Okay, so I'm about to blow your mind. Our task is there's this object tasks that sits on the implant. Okay, so this is tasks is a member to the implant. It's a field. Okay, we need to get the tasks that are in that vector and take control of them as quickly as possible, and then release any locks that we have so that the beacon loop can do its thing. Okay. I'm going to show you a super performant and like rock solid way to do this that it's like 5 lines of code in C++, okay? So we declared our own vector, okay? This is a local variable in this function. These braces here define a scope Okay, so when I declare local variables in that scope, like in C, what happens? Yeah, they initialize at the beginning, that's when their lifetime begins, and then when the scope ends, they destruct, or they go away. All right, so we had this task mutex thing, which is helping to lock the tasks vector. There's this amazing object called scope lock. It's like really simple to write your own, but basically it acquires the lock in the constructor and it releases it in the destructor. It sounds simple, but like it is one of the coolest things in programming languages, is this idea that you tie resource allocation to initialization and then you release it in the destructor. And there are a couple of reasons for this. I could nerd on out about this for about an hour. But basically, we're guaranteed that once this statement executes, this will wait for the mutex to open, right? Because it's going to call lock. We can do whatever we want in here, and it will be serialized access, like safe access to that task. And then when we fall out of the scope, no matter how we do it, if an exception gets thrown, whatever, we return early, the destructor gets called, and we will always release this lock. I'm sure you've like debugged something where you're in a deadlock and you're like, oh my god, like why is this happening? And you're like, oh, I returned early and I didn't release the lock. Like, damn it, you know. That'll never happen here. It just can't happen. Super cool. And then you've got this this function called swap, which basically moves the elements from one vector to another, and it's crazy fast because it's just pointers, right? So this code took a not thread safe container, the vector, and made it thread safe by basically taking all the tasks out of that thing at like lightning speed under a lock and then releasing the lock in a super fast way. It's pretty awesome, right? You had a question?
Is stood scope lock different from a lock guard?
It is. One of them's movable, and I can't remember which. Great question, though.
Doesn't matter.
Yeah, I think scope lock is not movable. I'll have to check that, though. It's punking me. Okay, cool. So we've acquired the tasks. They're local now, so now we don't have to do anything under mutex. Like, we're good. There's no thread safety issues, right? This is really cool. We're going to take you into std variant and std visit, and you're going to be like, I will never write tasks in another way. You should for OPSEC reasons, but like this will be your preferred way. You save this one for like the good tool. So we're going to make a tasking system where essentially we can define new tasks, and as long as we expose a run method, this is just going to work. We don't have to change our dispatch loop, if that makes sense. So if you have a new task, whatever it is, load DLL or whatever, you don't have to do anything except write a new task and like plug it into the parsing framework. This service loop doesn't need to know anything about your new task. So think of this like generic code, basically.
Does run
yeah.
need to be const method?
It does. Here. It does.
Okay.
Yes. Yeah, that's a good observation. So, yeah, like you in your Lambda here, you want to make sure that the that your qualifiers here make sense. So maybe that doesn't make sense to have it be const here. Totally design decision. I think it's probably better not to have a constant. Yeah, so this is basically going to execute the run command on a task. And the cool thing is it's going to do the type checking at compile time. So we're going to make sure that this thing actually has a run method, actually returns the right types, and will never get like a method not found exception. That just doesn't exist. Super cool. And then we're going to do this trick again, right? Scope block. So we're going to do something here to lock our results container, and then we're going to add our results. So this is we're going to make a UUID, cast the UUID into a string. This is the syntax for property tree to like access the contents element. Essentially, yeah, great way to think about it is an in-memory registry. So we're going to set the contents and set the success value that we got from our task. And that's it, man. We just like dispatched a task and we saved it into a results object in a thread-safe way in like 4 lines of code. Right? Obviously, there's some like reading to do to figure out how to use these objects, but like super clean. And then we go to sleep for a second. Pretty straightforward.
So notice your results is always a
Yeah.
string method as opposed to like binary data.
Yeah. Total design decision. So we, for simplicity, are using JSON over HTTP as like our wire protocol. So I just designed around strings. I wouldn't recommend doing that probably in like anything that's sophisticated. So there's all kinds of like cool marshalling frameworks and things that you can use. I'm sure you're aware of. But yeah, like the string stuff is just for simplicity. So we just talked through at a high level what the beacon loop and the service loop look like, and we saw how amazing the facilities are in C++ for dealing with multi-threading in a like super fast and safe way. So let's dig into how some of the nuts and bolts are working a little bit more and demo some other features. So in the beacon loop, we had 2 important methods. One was sending results and the other was parsing tasks, right? So let's talk a little bit about the send results method. So we see the same trick here where you're making a local. First, let's talk about the no discard. So C++ 14, I think maybe in C++ 11 there were some attributes, but they've been adding more and more to the language as they go along. These are entirely eliminated at runtime. These are simply annotations that give the compiler more information about your intent. So there are a couple of really cool ones and a couple of like super obscure ones. One of the really cool ones that you should get in the habit of using is this no discard. So basically it says like if I don't bind the result of this call into a variable somewhere or use it in some way, it'll throw a compiler error because I've expressed that you shouldn't get rid of this thing. So in this case, like the CNC server is like giving you tasking like you shouldn't drop those on the floor. So we use the no discard attribute as to get your mind noodling on this a little. There are some like attributes that are coming down the pipe for in a switch statement or in an if-else statement, annotating which branch is more likely. Which is like, you think about it, you're like, holy shit, that makes a ton of sense. Like, because now the compiler can make optimization decisions around going down that path more likely than the other. It's that kind of stuff. It's super, super cool. I think we're going to see a lot more attributes getting included in the language over time. Here you see the same trick as before with the tasks. We're going to rip the results off of the object so that we can do things in a thread-safe way. So we make a local one here. Instead of a vector, it's a property tree now. We do the old scope lock swap thing, super fast, and now we have a copy of our own results. The nice byproduct of this is we just cleaned out the results object, right? Because we swapped an empty one for the one that has it. And then this is the main reason that we use property tree. There are other like JSON serialization libraries out there, and for OPSEC reasons, you'll probably just, if you end up using JSON, you want to use all different ones. But this is one that's in Boost. There's the API is the following. You give it what's called a string stream. I'll talk about that in a second. And then you use this write JSON function in the property tree namespace, and it'll take the results, your property tree, and serialize nice JSON out of it for you. It's super cool. So a string stream, there's this whole part of the standard template library, part of this standard library that deals with I/O, and they're called streams. They have this kind of like interesting looking syntax where it's like two angle brackets going in either direction. Basically, the string stream allows you to write data into it indefinitely, essentially, and it'll just keep accumulating stuff that you write in. Boost property trees written in a way that that's how they decided to handle I/O. So we give it one of those, and then to get a string out of it, we just call this stir method on it, and we're good to go. Any questions about that? Pretty straightforward, right? It's like a similar analog to how we did the tasks. Again, it's hard to overstate how much simpler this is than trying to do something like this in C, where you're like manually managing locks and moving pointers around and stuff. And that's it. We just we return this make request thing that we'll talk about. So make request is responsible for actually pushing the HTTP request over the wire. Lots of ways to do this. Like if you're not cross-platform, you may want to, you're in Windows, maybe you want to use WinHTTP or WinINet or one of these like, built-in syscalls for handling this stuff, or maybe you have an HTTP library that you want to use. I told you we were going to write a cross-platform implant, so we'll do it in a cross-platform way. Basically, what did we pass into this thing? We passed in the host, right? This was either the IP address or the host name. The service, which is either a service name or a port. The results string, and then this I/O context thing that we haven't talked much about. So we need an HTTP post with this JSON data in the body. So we build our own string stream, and we're going to start stuffing things into that to build our requests. And then we're gonna do that. We're gonna build a request. We make a string out of it. We're gonna connect to the server, and then we're gonna write the request to the server. So let's talk about how we build the request. So this isn't a fancy HTTP library, right? Like we're a little in the weeds here. But if you ever looked at HTTP raw traffic, it's really not that bad, right? You've got your 2 lines here that indicate what the verb is, the HTTP verb, the resource that you're trying to interact with, your version of HTTP. If it's 1.1, you need this hosts line, and you have some headers, right? Here we're not doing it. This is not InfoSec. This is just HTTP programming. We're going to put in our size for our payload, and then we're going to write the payload in, and then we're good to go. Is this something I said? So we built the request, we got the stream, now we're going to connect to the server. So this is how Boost ASIO works. It is an incredible framework, but it's a little daunting because asynchronous I/O is hard. They try to make it pretty easy, but it's very heavily templated. So you're going to want to pull out the documentation and figure out how to use it. Crazy high performance, really, really amazing framework. But the way it works is you build a resolver, and this thing is going to be responsible for locating the endpoint that you want to talk to. Everything gets an I/O context pretty much. You call resolve with your host and service. It, like in a platform-specific way, tries to find the endpoint that you're looking for, or a list of endpoints that meet your criteria. In this case, if we pass it a host name, it'll do DNS requests. If it's an IP address, it won't bother. That sort of stuff. Then you create a socket, and you connect. Really not too bad, right? This is synchronous here. You can do this in an async way. It's just much more verbose. And if you're actually going to do this for real, there's a library also in Boost that builds on top of Boost ASIO that's called Beast. This guy Vinny Falco, really smart dude, wrote this library where it'll handle a lot of the HTTP stuff for you. So if you're actually going to do this, check that library out. Cool. So we sent the response. We sent the request. Now we're going to read the response. So we did something a little nasty in this HTTP request. Does anybody know what this header does?
Doesn't keep the connection open.
Bingo. So the remote, if it complies with what that header is supposed to mean, is just gonna like bounce the connection on us, which Boost ASIO will say like, that was rude, and it'll give an error code, which turns out to be 2. So we're just gonna ignore that if that comes in. So we wanna get the error code. To your question about whether or not to take exceptions, Boost takes a really elegant approach. So they have basically 2 versions of every function that could produce an error. One function will take an error code object like this as an out param, and the other will not. The one that takes the error code, if the function encounters an error, will set the error so that you can check it without exceptions. If you don't pass the error code, it will throw an exception. So it's cool. It allows you as the user of the library to decide whether or not you want to handle it as an exception or not. I think it's a neat design decision that like you could use yourself if you're designing like a library or a framework that others are going to use. So.
Is that via overload or via name of the?
Overload. Yeah, and so basically we do some version of both of these things by passing an error code, checking to see if it's the error that we don't care about, and then throwing if it's not. So it's kind of just a cool example of like exactly the discussion we were having. Does that make sense? Cool, so we just sent the response. That wasn't too bad for like how high level HTTP is actually. Now we have to parse the response, which is our tasking, right? So we sent the results, we're gonna get the tasks back. How do we do that? Okay, well, we're going to build a property tree out of this response that we got. It's basically the exact opposite of write JSON, right? We create a string stream that we're going to read from instead of write to. We build a property tree, and then we call this read JSON function, which is going to take the response string stream and then write a property tree out. So now we can just interact with this thing as a dictionary. Super cool. This is kind of fancy. So C++ has this thing called range-based for loops that are super cool. It's similar to how for loops work in Python, right? Where it's like for x in whatever. C++ has that. So if the object that you are iterating over exposes certain methods, the for loop will just do the right thing to iterate over each value. There's something else that's super cool in here that you may have noticed. This is called a structured binding. So this const auto thing with the square brackets. Structured bindings are cool because they'll unpack a struct, essentially. Anything that has ordered elements that it can access. There's a couple of different rules. It's a language level thing. So this is basically going to iterate over the property tree, and it's going to pull out the keys and the values directly all in one statement. Some people might not like that, but like I think it's a pretty cool feature of the language, the structured bindings. It's especially cool if, you know, for example, mostly syntax sugar, but in C, oftentimes you'll see in syscalls the return value will be what? An error code, right? And if you have to take things out of a function, you do this thing that's unnatural, but like as C programs are so used to it that it doesn't feel unnatural anymore, but we have like out parameters, right? So you're like packing all of these references into the function signature just so that you can get them out of the function. That's weird. Like it's weird to newcomers, and it's a weird way of doing things that's basically a reflection of the assembly that gets emitted, right? I can't return this thing in a register, so I'm going to make you like, do this weird thing in the language. Well, structured bindings allow you in C++ to do a natural thing, which is parameters are inputs to a function, return values are things that you return, right? Crazy idea, but 2017 we got there, so that's structured binding. It's pretty cool. Okay, so now we're going to talk about how to create a task from a JSON entry. So we've got the string response from the server, we parsed it into this P tree, we're iterating over the elements of this tasking dictionary. How do we create tasks out of this thing, right? So, unsurprisingly, since we're interacting with a container that that's accessed by 2 threads, we're going to do the old scope block song and dance, right? Task is a vector, right? Vectors have this cool method called pushback, which basically adds an element onto the end of the queue. The vector. And what are we going to add? Well, we're going to add this thing that comes back from a method called parse task from. And we're going to talk about that in a second. This lambda we'll also talk about. Okay, let's just remind ourselves quickly what the tasks look like so that you can refresh your mental model. So it's a list of dictionaries, right? So all of these tasks will have an ID. All of them will have a key called type, and we have to do something with this on the implant side. And then it's basically a bag from there. Like, we can put whatever keys and values we want. We just need to make sure that we put the right things in there for the task that we're going to build out of it, right? So, for example, in this one, this is going to be like a recursive list of a directory. Maybe we want a depth parameter that says how far to go into the directory when you're traversing it. For our execute, obviously, we're going to want some sort of string field for like what command do you want to execute. Maybe we have a configure task that configures the implant, right? Here we can set whether it's running or not and what its dwell time is, that sort of thing. So like the question of what's in a stage 0 is kind of like, when you see it. There's no strict definition that I've ever seen passed by a committee. This is what I'm going to put in this one, so like we can have a discussion about it or move on. It's up to you guys. So we're going to put 6 tasks in there, and I chose tasks that I thought gave a reasonable representation of like different stuff you might want to do. Also, conveniently, things that I can do in cross-platform C++, but we won't linger on that too much. So I'm sure with this present company that you've seen a wide range of ways to do tasking, how you store tasks, how you interact with them. Lots of good options, right? There's no universally right answer. And the wonderful thing about doing C&O development is, even if there was a right answer, you still sometimes want to do the wrong one, right, for various reasons. So I'm going to show you one very elegant way to do it in modern C++ that uses this really, really cool type called std variant. How many of you guys ever used a union in C? Std variant is a type-safe union. I'll show you how it works. So basically, it's a templated type. So you tell the variant what the realm of the possible is. Like, what are all of the types that you might be at some point, right? And it stores these at compile time. Or knows this information at compile time. So it can do all the type checking that in the world because it knows the types that it could possibly be. The way that you generally like interact with std variants is with this with this std visit function that I'll show you. Basically, like, you apply some generic code to the variant, and the compiler will generate the correct code. There's another similar object called std any, which is less restrictive. You don't have to tell it at compile time what types it can be. I chose variant because we know the tasks that we're going to take. So, but that's another option is any. Okay, so this is a syntax for basically like, hey, this huge cumbersome definition here, I don't want to be using this all over the place. Please use this. It's like a safe version of a pounding drum, basically. It's a using syntax. Or if you've ever seen typedef, typedef is for several reasons like almost deprecated. You should use using instead of typedef. Anyway, so this is how we define our task. And then you might ask, what are all of these, right? Well, we get to decide. So like when you design a template, we get to decide what is in a task. So each task implements a run method that you saw why, right? We're going to invoke that in the service loop. And then run is going to return this like result object that we'll design a bit later. And then the service loop uses visit to invoke run on each of the tasks. Pretty straightforward. Pardon the terrible pun. We're going to look. We're going to look at the service loop. So this is what it looks like. You essentially pass a variant in and a lambda. So here's the variant task, and then we're going to pass this this lambda in, which says, "Hey, visit. I want you to apply this function to this variant and give me the result." And you'll see this guy here is a structure binding, so we can unpack ID, contents, and success. There's a little bit of a spoiler alert on what's in the results object. The task declarations look like super similar. Let's just go through them really quickly. We're going to have this little key object that we'll get to. This is useful for parsing the JSON. Essentially, like associates a human readable string to the type. And I'll show you how we're going to just kind of iterate through all the possibilities and construct the correct task out of that. It's got a constructor that does the same old, store member variables trick. This one actually I think is missing ID here somehow. Oh no, it's up here. Sorry. And then we're going to have this run thing, right? And notice the no discard attribute. Same thing for delete. The only difference is the key, really. Put is a little different, right? Because it's a different task. So for put, we want to like write a file to disk. So we want to store the contents of the file that we want to write. So the constructor changes, but notice that the run command and the UUID don't change, right? Here we've got the recursive directory list. Here we take in a depth, right? Execute task has a command instead of a path, that kind of stuff. But notice that the run and ID don't change, right? That's the interface for this variant. And here's the configure task, which is where that lambda comes in. So the configure task is interesting, right? All the tasks so far have interacted with the system. They're doing stuff to files, they're executing commands, whatever. Configure has to like kind of hook into the implant a little bit, which is why I thought this would be a cool task to talk through. So in our really, really, really simple implant, there are like essentially two settings, right? One is the dwell time, how long to wait in between beacons, and the other is the whether it's running or not, right? So this task needs some way of changing the implant. A lot of ways to skin this cat. One way is to pass it a lambda that says, hey, all I need you to do when it's time for you to configure is invoke this lambda with a configuration object, and I'll take care of changing the implant. So if we look back, see this lambda? You pass it a configuration object, and it will set the dwell and the running, right? This is one way to do it. Lots of potential ways, but you could even pass it a reference to the implant, right? That would be another way to do it. That's potentially a little less encapsulated, but totally viable. And you're also tying the task to that particular implant, right? Maybe this is a library or something. But cool. Okay. Now we need to talk about how do we take JSON, right? Like, so we're iterating over these like text data. How do we make tasks out of that, right? So I just showed you the the class definitions so we know what they look like. How do we create tasks out of this is an interesting question. So here's one way to do it. First thing is we're going to extract the task name out of the JSON. This is just kind of the syntax for Boost property trees. No, not rocket science here. You pull the type out of that JSON blob and the ID. So we just pull those out. Pretty easy. Construct and return the task. No surprise here. This is just a simple if-else. Notice that I use the that key member, that static member on the class, so that we can compare. See these? See these keys here? So that way, if we change the, what we want to call the execute command, you just do it on the class rather than in some like dispatching code. And yeah, you just pull out each of the elements that you need to construct the object, right? Not rocket science. A couple of ways you could do this, right? Like you could even, if you're comfortable with the tasks being a little bit more heavyweight, you could even like just dump JSON objects into the task constructors and they can handle it. All design decisions. These are all kind of up to you how you want to do it. I picked this way. Pretty straightforward. Any questions about how this works? Notice we return a task though. In some ways, this is similar to type erasure, right? Like or a union, right? Like we've parsed out a task, and then we're returning a generic task object to the framework. Because the framework, the implant, doesn't really care which task it is. It's just like, I'm going to invoke run on this thing. It's going to give me a result, and I'm going to send the result back. That's all I care about.
Are there any performance or any other implications for using a variant instead of inheritance here?
Instead of a what? Instead
of inheritance for your tasks?
Yes. So if you use virtual functions in your hierarchy, there's a modest overhead associated with indirect function calls that will absolutely not matter in InfoSec contests. Like you're talking about within like microseconds of each other, right? But there is a performance penalty for virtual function calls. Sometimes there's some really interesting work that's going into linkers being able to link time optimize away virtual function calls, which is super cool. Just know that that's there though. Okay, so as we saw, all of this expose a run method, and the whole point of this, there's like a pattern name for this. I think it's like the command pattern or something. I don't know. But like basically you set an object up to do something and then like invoke a method that you don't know anything about how it's set up really, but you just know that you invoke the method and it gives you a result. Is that right? Command type application controller. Maybe. Yeah. So what's in a result? Let's remind ourselves when we designed our wire protocol. Super simple. UUID is the key. So like there's asynchronous tasking here, right? Like we're pushing tasking down. The implant will go off and do its thing in a service loop. Might take a couple of minutes, like if you're running, some really intensive task, like a recursive directory walk, for example. So we want to keep track out of band which task it's reporting on. So we'll just take the ID as a UUID, as the key. And then the values will be content. So if the task wants to tell us something about, if it's a net stat, for example, like we want to see the dump of that, or if it's a get file, put the contents in there. The way this is designed, by the way, it won't work very well with binary files, but that's left as an exercise to the reader. You'd at least have to like encode it somehow for the JSON to work, right? Use BSON maybe. Yeah, so pretty straightforward. The definition, one definition, looks like this. This should be a braced initializer here. Just stores ID, contents, and success. Really straightforward, like super straightforward. So, implement a task, do stuff, return a result. Let's talk about some of these. So, what we've been talking through so far has been a lot of like design things and like fancy C++ patterns and different kinds of like classes you can use. This is actually tactical level stuff that like if you just need to like write a file or do a dir walk or something and like not totally embrace like the entire religion of modern C++, you can just incorporate some of these tactical level things into your tools, and there's no problem with that at all. So let's talk about the get task here. So its responsibility is to get a file. The canonical way to do this in the C++ standard library is with these things called if streams, in file. So you construct it with a path. Remember, this is a field on the object, a const field. If the file is not open, again, to your question of do you throw an exception or not, this is something I, as the developer, anticipated may happen quite a bit. So I decided not to throw an exception. I just want to return the result saying, yep, it did not, you did not succeed here. A lot of ways you can read from a file. My favorite way is to use the algorithms, the STUD algorithm, standard library algorithms. So the way you do that, you make an O string stream. So this is a string stream that you can write into only, can't read from it. And then there's this STUD copy, which I recommend like you learn a little bit about how this works. Because it's awesome. It works with all the like containers and streams pretty seamlessly, but it also has backwards compatibility to raw pointers. So even if you're like interacting with a C library or with syscalls, you know, like we're interacting with the operating system at a pretty low level, you can still use STUD copy and a lot of the other algorithms, and it's a very nice, safe way to do it. There's also a variant called copy end. So if you want to think of the analogy to like string length, right? Like you want to have a limit to how much data you're going to copy.
What's the second argument?
The stream buff iterator, guys?
The second.
Yeah. So this is kind of clunky. This will get fixed in C++ 20, but basically copy takes 3 arguments: a begin and end iterator for the source, and a begin iterator for the destination. By definition, for an iStreamBuff iterator, this basically like adapts the file into an iterator. When you default construct it, like you pass no argument, this is by definition the end iterator. So when it does the comparison, when STUD copy does the comparison, it says, oh, I'm equal to the default, I'm done copying. So this is going to copy the entire file into the string stream. And then we can return our result with the ID, the contents of the file, and true, because we succeeded. Any questions about this?
Does file not have a begin method?
File does not have a begin method. Yeah, because it's a stream. So you can always adapt streams into iterators, and in some cases, I think you can go the other way too. So just so you know, C++ 20's got this thing called ranges, which is awesome. Basically, like when you learn how algorithms work in C++, you have to learn a lot about iterators, and like they make sense and they're elegant, but like you don't want to have to deal with those when you're programming. You're like, no, I just want to copy this thing into this thing. Like, why do I have to tell you that it has a begin method, right? In the same way that in a for loop, you know, you pass I showed you how range-based for loops work. Or in Python, you just like for x in whatever. It has like list comprehension. Like we want to get list comprehension for C++, and in a lot of ways we're going to get that in C++ 20, so it's pretty cool. Got that going for us. Put task is very similar, except instead of an IF stream, we're going to use an OF stream, right? Again, check if it's open. We anticipate this. We may have permission issues or whatever. So we'll handle it with error checking, and here's how we can copy our contents, which is a string. It's a string member into the file. So we use a stream buff iterator for the file, but we use these begin and end methods. Note, interchangeably, you could call it .begin or .end. It's just preference, really. You should use, if you're writing library code, you should use these because it is more generic than calling .begin.
When we exit this context, is the file just going to immediately close?
That is a great point that I didn't bring up. Thank you. Yeah, so all of the standard library classes embrace this RAII concept I was talking about, where when you construct it, it's acquiring resources, it's doing memory allocations and that sort of thing. And then when it dies, when it goes out of scope, magic happens and all of that stuff just gets released. And it's better by far than garbage collection, right? Because it's deterministic. Like when you exit the scope, when you throw an exception, you return early, all those destructors get called and all your stuff gets cleaned up. So like I know, I'm your support group, man. Like I know that when you've written C, especially system programming, you've got go-to statements that are like kind of like stacked in reverse order so that like, oh wait, I errored here, so I have to clean up, oh okay, I only clean up these resources, right? Like there's this craziness that you have to do. C++ takes care of all that for you. Okay, so the next task we have here is the delete task, which is a little bit different from the other ones, in that the system call that it's making via the file system std library API is std file system remove, which accepts a path argument. In this case, the member variable path, that's a string. And if it's unable to remove, it's going to throw an exception when we use this this overload. And so if it doesn't throw an exception, we know that it was able to remove the file, and we can return a result that says, hey, I was able to remove the file, it succeeded, and then obviously the result. If it does throw an exception, though, we catch that exception, we report the exception as part of the result, and then we report false that it was unsuccessful, and then also report that ID. Here we have the list task, which, as you can see, is a little bit more verbose, but it's actually not that bad. The std file system API has a thing called the recursive directory iterator. So we construct one of those. We pass it the path for like the root of where it's going to start during the recursive search. And then we can pass different options. So here, instead of it stopping whenever it doesn't have permission to recurse into a directory, it's just going to skip. So that's what the file system directory options skip permission denied means. Then we do a check once we've created the iterator and the string stream that we're storing the results in. And that check is to see if the iterator is equal to the default constructed recursive directory iterator. And this basically just says, hey, is the directory empty or did it not exist? And if that check is equal to true, we just return a result that says basically I was not successful, either I couldn't open it or the directory doesn't exist. Okay, so once we've done all that ceremony, we can start entering into this this while loop you see here, which is going to check and see if our iterator is done. That's the not equal to the default iterator, and then we see here these, and then we see here there's the visit each entry. So in visit each entry, we have a little try except block here where essentially we just pull the path out of the iterator and then we increment it, and that's it. I have here the execute task, and the execute task basically is able to execute an arbitrary command that we pass it. What I chose to do here was to use the popen API because it has a low-level syscall field to it, and it allows us to explore one of the really neat ways that you can interact with C APIs from C++ and make sure that you're cleaning up resources appropriately. So in here you'll see that we create an array, and that's a 128 byte buffer of characters. And then you'll see here we've got a std unique pointer, and this is what's called a smart pointer. So it has the ability to essentially manage heap allocated
objects for us, and it's an RAII object, resource acquisition is initialization. So this basically means it'll acquire the resource, in this case, heap allocating something and initializing it. And then whenever this object falls, its lifetime ends, it will destruct that object appropriately. So we can kind of use this cool little hack here where basically we overload the destructor functionality of that, and we're able to essentially say, hey, unique pointer, when you destruct, invoke this command given the pointer that I passed to you. So you see here, we've got a unique pointer where we are creating, we're invoking popen by passing in the command. This will return a file handle. So the unique pointer will hold that file handle. And then you see this second argument to the constructor is called pclose. And what that's going to do is essentially when the unique pointer destructs, it will invoke pclose with the file handle that it got from popen. And that makes sure that no matter how we return from this function, if we throw an exception and it causes stack unwinding, if we return early, we're always going to close up this file handle. In this case, the handle to the process that we're creating. If for whatever reason we weren't able to invoke the command, so popen returns a null, this check if not pipe will return true, and we'll throw a runtime error and say basically failed to open pipe, and the tasking framework as you'll see that it'll get caught later on here, and then we'll return a result that says what the exception is, in this case that it failed to open the pipe. And that the task was unsuccessful. If the popen invocation is successful and pipe is non-null value, we enter into this loop where we call fgets to pull data from the pipe into that buffer that we created. And while that data is getting buffered in, we write it into the results string until there's no more data left. So fgets returns null, and then we're going to return the results by passing all the data that came out of that process, return true that it was successful. Finally, we have the configure task, which is by far the simplest of all the tasks. It actually can't fail because of the way we've designed the setter invocable function here, but essentially we pass in configuration object that is comprised of the mean dwell time and the Boolean for whether it's running or not. And then once that setter function returns, we just return from the run method result object that says, hey, I was able to configure the implant and I was successful. All right, so let's recap a little bit here. So what we have is a stage 0 beaconing implant that has a beacon thread that's responsible for pulling results out of the queue, pushing the results to the command and control server, pulling tasks from the command and control server, and pushing those into the task queue. And then essentially it goes to sleep and wakes up after its dwell time's elapsed. So it's responsible for shuttling data back and forth. There's a second thread that's called the service thread that's responsible for first pulling tasks out of the queue, executing those tasks using the command pattern that we designed around std variant, and then pushing the results from those invocations into the results queue, and finally going to sleep for some time before it goes and checks for more taskings. The tasks that we support are get a file, put a file, delete a file, recursively listing a directory, executing a command, and finally configuring the implant. And now it's time for a demo. All right, so you can see here we've downloaded all of the demo code available on GitHub and compiled it according to those constructions and built a folder that contains the CNC server, that's the Python script, the compiled binary, that's the implant, and then the sample tasking, which is that JSON file. So you can see the tasks here contain examples of each of the different types of tasks. So here we've got a list command that's going to try to list out my home or my downloads directory to a depth of 2. We've got a put command, which is going to put a text file called hello world in the current directory that the implant's running in. We've got an execute command that's going to run netstat. And then we've got a get command, another one for my public key for SSH. It's going to try to delete a file called test file and configure the implant to dwell for 5 seconds on average and maintain running status. So let's create this test file just so that we can demonstrate that delete file works. Okay, so what we're going to do here is in another terminal window, we're going to run the command and control server. Okay, so that's running there. It's bound to port 8000 by default, so we're going to run our implant with the option to connect to port 8000, and the default host is localhost. So we're going to connect, and we see a whole bunch of activity here. So I'll exit out of this. You can see that in the command and control server, there are a whole bunch of HTTP posts that come through. And then you can see printed out the console here, the implant just reporting that it got some responses back from the server, which of course it parses into task and then sends its results. So if we look in here, we see a whole bunch of results files that get printed from the command and control server. You'll notice that the test file's been deleted out of this directory, and also that hello world is present. So you can see that it successfully dumped the contents of that file into here. And if we cat this results file here, we should be able to see the implant coming back with a whole bunch of information. So you can see here that whole bunch of data came back. This is probably the netstat here. Yeah. So tons of information came back to the server from the implant. And then, of course, you've got the other taskings for writing files, configuring the implants, and so on. So this concludes the talk. You can download the code from the GitHub link that you see here and reach out to me if you have any questions. My username on Twitter is JA Lospinoso, and my direct messages are open. So if you have any questions, you can hit me up there. Thanks so much.